Okay, welcome to the January 17 NTI Day video. We're going to be working on topic 2.9 here. Before we get started, just wanted to say make sure that you check out the Schoology agenda to make sure that you do everything that's needed for today. So let's get started. So we're working with logarithmic expressions today. This might be a new concept for some of you. Maybe this is something that you've seen before, but the important concept that we're working with just previous to this was inverses. Right? And the important concept today is that every operation has exactly one inverse operation. We learned inverse operations because they allow us to solve equations using various operations. So once again, the inverse operation of addition, if I was going to solve this, I would minus 3 on both sides, and because I need to do subtraction, it's inverse operation. Same thing with multiplication, that is division. And then for cubing, I would do the cube root, right? And all of these are really helpful things to know because I'm able to isolate x and get the value here. But this guy right here that I just put a star beside is where we run into problems, right? I have exponentiation when I have an x in the exponent right here. If you haven't worked with logs yet, there's really no way other than guessing and checking and then plugging in your calculator to where you get close enough to have a semi-rounded answer to get here. But what we're learning about today is exactly the thing we need. That's where logarithms come into place. Okay. Recently, we've learned the exponential functions and their properties. We would like to solve equations with x and exponent, right? Like exponential functions, we got x and exponent, we want to solve it. And the big idea here is just as we can write rational numbers in decimal or fraction form, we can also write equations in exponential or logarithmic, and that's how you say it, logarithmic form. These forms create equivalent statements that represent the same claim. Like what this is saying is we're just rewriting it. These are the same exact equations. It's going to look a lot different. It's going to look like, what in the world did you get that from? But it's just how this works, okay? It's the same problem. We're just rewriting it. And here, this is how you normally see it. You normally see it like this right here. B to the A equals C, and you would rewrite it in logarithmic form with this log guy right here, B in the bottom, C here equals A. Okay, and remember, let's go over some vocabulary here. That B is your base, this is your exponent, and then here, this is usually what you would call your answer. And notice here, once again, oops, I'm ahead of myself here. My exponent's over here. And this is the answer. Okay, A, B, and C are just arbitrary things that we have used to say this and to order it. And one way to remember the order for logarithms is that logs are base, answer, exponent. Base, answer, exponent. And of course, I'll go through a couple problems here of how to rewrite them and everything that you're going to need to do here. But that's the general form that we're going to work with. But I'm going to show you a way to draw it out that'll make a lot of sense every single time. And note, for the notation here, if the base of the log expression is 10, this is the common logarithm, and it's written without a base. So log 3 could also be written as log base 10, like it shows here. Just the same way that you could write square root or like the radical symbol with a 2 there. We just normally have it as a square root. That's what we know it to be. If we just say log, we're saying log base 10. So let's get into it, some examples. What's this all talking about? So convert the following equations from exponential form to log form. And on these examples, I'm just going to do the first two always, and then, or at least just two of them, and then have you do the other ones by yourself. So we're going to do C and D together. So right here, the way that I always remember when I have a log is I'm going to have a log, whatever my base is. So I've got a box here, equals a box here, okay? The way that I like to do this is to set it up like this every time and draw it out. And I'm going to draw an arrow from the base to the other side of the equal sign, say to the power of, and then a line from here to here and equals, okay? This, I'm putting a bunch of stars here because this is the key thing for every bit of it, okay? This is how I remember it. This is, logs did not make sense to me in high school, and now they do. I came up with this way to remember. Like, I don't know if somebody else came up with this before, but this is how I remember it always, okay? My base is to the power of, and it equals something. And this is kind of just how you read your exponents out loud, right? So if I was going to read part C out loud, I would say R to the power of T equals W. Okay, now as I read that out loud, let's fill in what I have. So log base R to the power of T equals W. And notes, so the way to write this is not with all the arrows and stuff. Like, that's not the notation. This is exactly what the answer would look like. But this part that I add helps me remember where to put what. So the same thing here. I would write this. Notice they've got this flipped here. They've got this flipped. What I need to get is on the right side instead. So I'm going to flip that first. So e to the 3x equals y. And this e is a special number, kind of like pi. It's a special number that's undone by the natural logarithm. So you'll see, this is one that you'll see a lot. ln stands for the natural logarithm. Natural logarithm, okay? And what this has you do on the natural logarithm is it's just another way to undo the e, like the e. It's the opposite of the e. So what I need to do here is rewrite it. So log, I'll write it piece by piece. Sorry, it's been a snow day where I've been a little lazy. My brain's not working the best. So e, remember, draw my symbol to the power of, and once you get the hang of it, you don't have to rewrite it like this every time, but it's a helpful reminder. So e to the power of 3x equals y. So log base e of y equals 3x. And then from here, this is where the ln comes in. So right here, I can write log base e as ln. That's just what that's short for. That natural logarithm is short for log base e. So ln of y equals 3x. That's how I rewrite that one. Okay. And the delta math that you all are going to do is going to help with that. I'll make sure to make it a little shorter. So now let's go the other way. Going the other way is where this makes the most sense. Okay, let's say B and D together. And for the rest of them that I'm not showing, go to the answer key on Schoology and check that. So convert the following equations from log form to exponential form. Once again, I always want my log on the left side just because that makes my life a lot easier. This is where my arrows come into play. to the power of equals, okay? And how would I read that out loud? That's what I'm trying to get at with the arrows is 3 to the power of x equals y. 3 to the power of equals y. 3 to the power of x equals y. That's exactly how you read it out loud. That's how you write it. And then here, anytime I see ln, remember, I can rewrite this ln, I'm going to write it in black here, as log base e. Write the rest here, log base e of c equals 4. That's what ln is just short for log base e. And I'm going to rewrite this. So e to the 4th equals e to the power of 4 equals c. Okay. And once again, having this setup helps us evaluate expressions with logarithms. And we will do that here. So evaluate the following expressions with a calculator. So what I like to do in these scenarios is write it equals x, because that helps me think about what's happening here. So each time for each of these, you might write equals x and think about what x value would have to be here. So remember, draw my arrow every time to the power of equals. So 2 to the power of x equals 8. 2 to the power of what equals 8. So the output always is your exponent. Your output is your exponent. So 2 to the power of 3 is 8. So log base 2 of 8 is 3. Same way here. 5 to the what power equals 25. 5 squared, so that is 2. And then a fun one here is log base 10. Remember, if it's just log by itself, it's just saying log base 10 of 10 equals x to the power of equals. And please write it out like this every time for a while. I know it's cumbersome. I know it takes time, but I promise you'll remember it long term. So 10 to the power of x equals 10. What is that? Well, obviously, 10 has to be to the first power to be itself. Okay. All right, and for all the notes, once again, I want you to do all of the notes, but I'm just showing you some. Check the rest of the notes to make sure you're right on the important documents folder on Schoology. And then to evaluate these, on ones like A and B, there's just a log button on the front of your calculator. It should be on the left side. And if you have one with a different base, you would go to Math. And let me pull up a calculator really quick. Let me make sure I'm on the right thing here. Sorry. I know the app's somewhere. There we go. Come on, buddy. But while I'm downloading the app, it should be Math. I cannot remember if it's log functions or not. I should have this pulled up. My bad, guys. I don't have a calculator handy at my house. Or do I? No, I don't. Sorry for the awkward pause here. So let me log into my calculator app. Okay, there we go. So it's math, then you click the up arrow, and then it is log base. You should see it. It should say A:log base. There we go. I just wanted to make sure I was showing you the right place. So A:log base. And then for the last part of the notes here, I know I'm kind of all over the place. Let me just finish up here, and then I'll leave you on your merry way. Is one purposeful use of logarithms is when dealing with exponential data. Exponential data can be very challenging to display graphically because what's the whole purpose of exponential? Like, what does it do? It goes up really fast or down really fast. And you can see here, small jump, small jump, small jump, and then boom, by just a couple like parts down the road, we're already way up. Okay. So one thing that we do is that the graph on the left shows the populations using a normal scale. Because it's scaled into the millions, the data points representing the years 1620 through 1700 are almost indistinguishable. Like right here, these all look like the exact same point, right? It's hard to see any difference here. The graph on the right uses a logarithm scale. So this scale over here is base 10. So I'm going up by 10. So 10 to the 1, that's 10, 100, 1,000, 10,000, 100,000, right? So the jumps are not exactly equal, but they're equal in base 10. Using a logarithmic scale allows us to view all the data's points relative to each other, right? Like now I can see here on the 200th year and be able to distinguish from these front parts. Like all these parts that I'm circling here, compared the two. Notice how much easier it is when we use a logarithmic scale. So on this example, it says the population of data of English Americans in the current United States for the years 1840, 1860, and 1880 are given below. Plot these three additional points on the graph above. Okay, so it wants us to go through and plot these out. And what you can do is add to your chart here. We're going to do a log of the population values. So if you go in and do log base 10 of this number, so if I do log of this number, it's going to help us scale to the number that we're at. Okay, so log of that number should give me 7.2322, and on. For these, 7.4975 and 7.7006. So this is going to scale it logarithmically. So if I count, I should be right at 10 to the 7th and just slowly going up. So roughly for 220, I'm right here, somewhere in this ballpark. Once again, the answer key is going to have better points. I'm just slowly, quickly doing this off the top of my head. But that allows you to scale them relative to each other. So what all of this is doing is you're taking the log to scale. And I'm using that 7 for log, like that 7.232 I'm going to 10 to the 7th, and that's telling me where to put it. Okay. And then last part is one common type of graph with logarithmic scaled axis is seen below. This is not likely. It's going to appear on the AP exam. They stress this a lot. It is going to. So let's look at it. So plot the following points on the screen. So let's do A in red here. So 1, 20. So 20, you notice, is going to be right here. This is A. Let's do this in blue. B is going to be right here. So they're scaling. This is called a semi-log plot. We're not going to worry about all of this right now. But the way I count this is that this is 200. This is 300, 400. That's how I'm choosing this. So 300 is going to be right here. This is B. C at 3, 2. It's going to be here. Then in black, or we'll do in red again for D. 4, 15. So 15 is going to be halfway between 10 and 20 right here. Halfway between. So 4, 15 is going to be D right here. Okay, so you're going halfway between these lines here with them scaled like that. That's how you're finding the points. You just count the lines. So once again, the way I got 15 is this is 10, 20, 30, 40, 50. And we'll cover this more in class. But go ahead, take these notes. Let me know whatever questions you have via remind or email or Schoology, whatever you need. And have a good day.